on standard?
Mm-hmm.
Okay, good. I had mentioned when we first started this chapter, back in section 1, that there was a whole bunch of concepts I was going to spread out over the course of the 2 weeks. We're finally going to finish them off today because we didn't need them before today, and some of them, they're kind of heady stuff. So in the textbook, the author, I think it's kind of funny, gave them as homework questions. Now, how many actually have the ZIL? You look at it. Okay, so you're looking at some of these going, wow, these are kind of gnarly homework questions. Well, you know, more like PhD thesis homework questions, you know, deriving the gamma function, for example. And that's actually the lowest level of all the ones we needed to do. So our big goal today, really, here's our main goal today. For alpha being anything bigger than -1, and I mean any real number bigger than -1. So obviously we're interested in the integer, positive integer exponents, because that's probably the most practical. The other one we're going to be interested in are the halves. We're not really interested in the thirds or the √2s. All of them are relevant, but they don't translate as easily with the gamma function. So we're going to do this one. So I'm going to keep going back and forth to things that we've already done. So let me bring up something that we did, I think, on the first day. Okay, so on the first day, we did, I'm going to write them down. Then we did, I'm going to give you the progression that we did. And then we did this one. What it took to do the first one was the same math it took to do the other two, but we just changed some of the things along the way. So in this case, if you remember, what did we get?
Square root of pi.
We got square root of 2 pi. So then when I redid it later and I took out the half, it meant we needed an extra chain rule factor, so we lost the 2, so this one ended up being this one. And then we did this one, but if you remember now, because we multiplied by itself, oh, now I'm entirely in the first quadrant. So now my theta, instead of going from 0 to 2 pi, is now going to go from 0 to pi over 2, which divides this answer under the root by 4. So since it's under the root, it's square root of 4. So this one ends up being this. I'm not going to go through the derivation, but we did each of these. And so it's the result that we're going to use again today. So we did this early, we tweaked it to get this one, we tweaked it again to get this one. I don't need you to memorize it, just look back in your notes, we've already done it. But we are going to make reference to it today. All right, so we're going to start with this one, and I'm actually not going to really put any restriction on this one, okay? I am going to, again, make reference to other things that we already know. In fact, gamma function, I'll put that over here. We are going to use this one. And then this one, alpha, alpha minus 1. So alpha plus 1, alpha plus 1 minus 1. I don't need to prove this one. This is automatic based on that definition. Okay, and then that's what we used it to get the cool result that this is also equal to this. And alpha does not have to be an integer for this to be true. So we have that in our back pocket. Okay? So let's start with this one here. Now we're going to make kind of an odd substitution here. So right now, t is my independent variable. I'm treating s as a constant. Agreed? Now, generally when you do a substitution, think integral with x's. You first learn u substitution. when you were babies in calculus, but the use substitution is so limited because you have to have exactly the chain rule factor, or at least a scalar multiple of it, and in which case you don't always. And then in Calc 2 you learned, oh, I can make my variable x be a function of something else. Then I introduce dx being the other thing, and that's actually the main form. Then in Calc 3, when you did the Jacobian, you looked at it from that point of view. I want to make the substitution, which means I really want to say t equals 1 over s u. S is a scalar right now. So I don't need to have the chain rule factor sitting around. I'm going to introduce it because what's dt going to be?
1 over s u.
Again, I'm treating s as a scalar right now. Okay? And so over here, this is true if and only if t equals 1 over s times u. And you could write it as u over s. I'm treating u as the variable and s as the coefficient. Now here's the cool thing. When I have an infinite limit here. I'm going to make a substitution. Ooh. So you remember when you did u sub way back when, if it's a definite integral, you don't leave the old limits because it's not going to be true. You got to change the limits. But I'm looking at this going, as t grows without bound, won't u also grow without bound?
Yes.
And right now s is simply greater than 0, by the way. So will that change my limits of integration?
Nope.
No. And when t is 0,
It was also.
that's a good thing. I'm happy with that. I don't need to mess with my limits. So this will be this e to the negative u. What does this become?
1 over s u to the all u to
All to the alpha.
the du. Oh, 1 over s.
Do I have that right? 1 over su, all to the alpha.
1 over s.
And then 1 over s du.
Do we have to worry about, like, if either one of the functions, the exponential or the polynomial, if they're if they're like exponential, like we talked about bounded exponentials. Like, do we have to worry about that at some point?
No, because we're only going to use things that are of exponential order.
Oh, exponential order. That's
Yeah.
okay.
Remember, it was the big four. It's still the big four. Now, by the way, the exponential order guaranteed that I could do a Laplace transform on it.
So
If
we're
something that is not of exponential order, it doesn't mean I can't. It's unlikely, but there can be exceptions. All the exponential order, it was a necessary condition to be able to do Laplace, but I can do it in the other case. It doesn't happen, but we're not really looking at anything. There's only one function that we're actually going to look at. It's t to the negative 1/2. That's the only function that we'll ever use. That's not technically of exponential order, but that will still work because we're going to derive a formula. So let's manipulate this. U is the variable. Can I pull the s's out of the problem?
Yes.
Yeah, it might be a good idea. It might be easier to read. So how many s's do I have?
1 over s to the alpha plus 1.
Good. 1 over s to the alpha plus 1. And then what's left? Then I would have, I'm going to write it as u to the alpha e to the negative u du. Would that be okay to write like that? And I'm going to write it in reverse order because it's giving me this overwhelming sense of deja vu. See, this variable's here, it's here, it's here. Where else have we ever seen anything that looks like that? Any ideas? Like right there? Does it matter what letter of the alphabet this is?
Nope.
No, it doesn't. Remember, alpha is a constant. Ooh. Do you see it?
So
It's right there in front of you. What is this quantity right here?
gamma of alpha plus 1.
That is gamma of alpha plus 1. Cool. So what have we got as a result? I'll write it like this. This is how most textbooks write. They'll just write it as a quotient. Whoa. This is equal to this. What if alpha is a non-negative integer?
It's just factorials.
then I'm gonna see factorials, aren't I? So let me rewrite that then. Let me write it like this. I'll say z plus, because if it's, we already know what it is if it's a 1. I want it to be t to the first, second, third, fourth, fifth. What does that come out to be then?
And factorial.
Well, first of all, it would be what? Gamma of alpha plus 1 over s to the alpha plus 1, but for,
N.
I'm sorry, n plus 1. But if n is a positive integer, isn't my numerator n factorial? And isn't that the formula I've been allowing you to use for a couple weeks before we proved it? This is the first proof. There's going to be a different one that's actually a lot easier and quite a bit cooler. But kind of cool, huh? Could we have done this on day 1? Technically.
Yeah.
Yeah, but we would not have done anything else on day 1. We'd be spending all of our time, because those are some kind of scary integrals, right? But we know what the process is loosely. As you go further and further in math, if you're a math person, you do things like this periodically. You dust off results like this, and every time you do, you're going to be relearning it. You're not going to remember that we did every single step in this class. You're going to remember having done it. And then when you go through the process, you're going to go, oh yeah, okay, yeah, I wouldn't have known what the next step was, but now I remember doing it once. And as long as you understand the process, even though someone else is doing it, then you trust the result. Okay, that's a main thing. So that's a major result. Now, we have just proved this. This is an absolute mathematical proof based on everything we've said, but we're not nearly done.
Can I see the algebraic step for the 1 over s alpha plus 1? I didn't really catch this.
Because you're raising this to the alpha.
Yes.
So that's going to be 1 over s to the alpha.
Yes.
And then you have another s here.
Oh, so then when you take it out, you just get a
So it's
plus
alpha
1.
plus 1.
Okay,
Yeah,
thank
you're just
you.
adding 1 to your exponent there.
Thank you.
Everybody cool with that? Okay. So, this is beautiful. But we're not done. So here's what I want to do next. Where's my next one? I wrote it down. I can't remember what I was going to do next. We're going to do the... Where is it? Oh, here it is. Okay, sorry. I wrote down in stages what I'm going to do today. So now I want to do this one. Gamma of a half. I know gamma of integers. And I can write, right, gamma of a half. That's going to be a half minus 1. I know exactly what this is. I don't know what the answer is, but I know what to write. So this is this. Can I use integration by parts on this?
Why not?
No.
No, it doesn't reduce to
Yeah, because even though the u can go forever in each direction, the t, the exponents are going to go up or down. I'm never going to have that constant term I would if I had a positive integer. So no, I actually don't have an integration technique for that one. Not for that one. So everything you ever had in your life that you didn't have an integration technique for what was written, you used some form of substitution. Right? Could have been a polar substitution. Could have been a u sub. There's an infinite number of different substitutions. Turns out this one is not an obvious one. I want to let t equal u squared. And I'm just going to go ahead and let you finish it. Well, if that's the case, then dt is 2u du. And what would t to the negative 1/2 then be?
u.
That would just be u, wouldn't u to the negative first.
Yeah.
So far, so good? Now, careful. As t ranges from 0 to infinity, what's going to be happening to u? 0 to infinity. So again, we luck out, don't we? I don't even need to rewrite these as improper integrals because we're not actually evaluating. We just got them in recognizable forms. Once I wrote this, I already knew that was the gamma function. I don't need to actually integrate this. What we're doing is we're manipulating our integrals to make them look like things that we now know the answers to. So this one's gonna be a little bit tricky. So what am I gonna have here? Same limits.
U to the negative first.
U to the negative first are just simply 1 over U.
Times e to the negative u squared. Times 2u to the u.
No way.
Cancel. Now what am I left with?
E to the negative u squared.
If only I knew the answer to that one. Do I know the answer to that one?
1/2 square root pi.
It's right there.
You told us not to memorize these, but we
I
memorized
need
these.
you, no, I'm gonna show you which part you need to know.
Okay.
You need to know this. This is a straight up formula. You need to know this. That's a result. You don't need to know the derivation. It is pretty impressive if you could actually walk your way through this and explain it. What you have to understand is I was teaching for a very long time before I saw the derivation of this. And I didn't see it in a math class. So the derivations of these are not common. I think it's a privilege if you get to see one. I was lucky enough to see one, I think it was year 3 at San Diego State graduate statistics class. Never even saw it in a math class. And there were only a couple of the professors there that actually knew how to do this because it's not trivial, but it's so beautiful. When you see it, you go, oh, cool. Everybody knows the result, but it's the how to get there. And if all you know is the result, you can survive. But if you know how to get there, then see the 3 things I have there? All 3 of those are necessary. But if I didn't know how to do this one, then I could not possibly have come up with this or this. I would have had to rely on somebody else telling me the answer, and I'm not a big fan of that. Don't give me directions. I'm going to look it up on Google Maps, like this. I don't like being told things. I like knowing things and being able to figure it out. But that's a kind of a huge result. So how can I use this to my advantage? I think I can erase this stuff now. For example, I want you to know this. This is really important. But this was actually not very hard for us to derive. That's a good one. I don't need you to know these anymore because we only use these to get to the next thing. But none of these results are things that you're responsible for. But if you understand where they came from, then all of these results make probably a little more sense. I would like to do, how about, let's see, which one do we, hold on, I wrote myself in here. I want to do, oh, here we go. I want to do the Laplace transform of t to the 5/2 power. So that means I want you to write the integral, then I want you to evaluate all the way to the bitter end. Or maybe we can use this result. Which one do you want to do? The integral or this result? Yeah, I'm with you on that. I think that might be easier.
I thought this was only for the case when alpha was a positive integer.
Did we put any restriction on this alpha?
Okay.
No, we didn't. So no, that alpha. Now, what I said was, in reality, but by the way, everything I showed here, this is true. But if alpha is not an integer, or at least halves, I won't be able to go any further. If your alpha was 1/3, you could still write this, but you would never get down to a specific value. We just derived that the gamma function of a half is this. I don't know what the gamma function of any other fraction, a third or a fourth or a fifth. That's not practical because the substitution required to get there would have been pretty gnarly. Now, you've decided on your own to come up with a gamma function of 1/3 and to do all this. Is it possible you can complete it and give me a value? Yes. It would be a lot of work. Would it be useful information? I don't know if it'd be useful. I don't know if you would ever run across any need to have thirds or fourths or fifths. But see, I would do a similar kind of thing, wouldn't I? I'd do a similar kind of substitution, but the resulting integration still might not be able to do All right, I still might not be able to go anywhere. So we're going to limit it to what we can actually evaluate or halves and positive integers. But that formula, this is always true. This is always true. It's the fact that if alpha is not halves or positive integers, I just won't be able to give you a number here. I can write this formula. Always true, but again, I'd be stuck in the logger. That'd be kind of like telling you, you know, I have a trig function, I want you to, and now you know all your answers are this, you know, the sine of the angle, but you don't have a calculator. You know the answer is the sine of the angle, you just can't actually ever give me a number because you don't have a calculator. That's kind of the same idea.
The exercise is left to
You can tell me the formula, just never give me a final answer. So how do I do this? Well, let's start with that. This is gamma of what?
5.
5 halves plus 1.
7 halves.
Okay. I was wondering how long it was going to take to get that part. Over s to the 7 halves.
Yes.
Okay, well that's not very helpful. I don't know gamma of 7 halves, but I do know it's equal to 5 halves times gamma of 5 halves. But I don't know gamma of 5 halves. But I do know it's 3 halves gamma of 3 halves. But I don't know gamma of 3 halves. But it is what?
Gamma of 3.
1/2.
It's 1/2 gamma of 1/2. But I don't know gamma of 1/2. Oh, yes, I do. It's right here. So do we have a final answer to this question?
15/8 times square root of pi.
So 15, can I put the root pi on top?
Yeah.
And then what?
S to the
8
7.
s to the 7 halves?
Yeah.
That's probably the cleanest form. It's kind of cool. That is the Laplace transform of a fraction, of a t to a fractional power. Now, the fraction had to be halves because I had to at some point get to this term here. Now, let's suppose hypothetically we just picked a different fraction, thirds. This would all be valid, and at some point I'd get down to a gamma of 1/3, and everything I said would have been correct. I just wouldn't have been able to give you a number. So we would leave it in that unfinished form. It is what it is. But we can finish this one, because we now absolutely know that's the answer. Now, is there a restriction on this?
S cannot be 0 or negative.
This is a Laplace transform going forward, therefore, how about just greater than 0? That would be the normal Laplace restriction anyway, but I kind of need it because these are square roots, aren't they? Oh, that makes even more sense in this case. Pretty cool. So, I said we have a lot of stuff today. We're not even to the main thing. This is all stuff that literally is still coming from the first section. I told you the first section we could spend 2 weeks on, and we literally have spent 2 weeks because we keep coming back to it. I thought this was all a little bit too much for the first day of Laplace transforms, your first introduction to do all of this. I just find it interesting that the author made that this was a homework question. Everything I've done today, each one of these things was a homework question. Derive the following, and I just sort of laughed because I'm thinking, I was pretty good in differential equations. I don't know that undirected I could have derived any of these. Heck, in grad school, I'm not sure I could have derived any of these just on my own without somebody pointing me in the right direction. They're kind of heady stuff. But now you know the answers. So let's now get to the next thing. Now the other day, we did this shift, the exponential shift. And you saw that when you had the Laplace transform of a product and one of them was exponential, you didn't have to do the integration. That just involved a shift. So what I want to do today, this is now the main goal for the rest of the class. Our f of t is one of our legal functions, and this t to the n is going to be a positive integer. Unlike the exponential shift, where that was easy, I could just literally write the Laplace transform of f of t minus a. Remember that? It was really easy. This is a little bit more involved, but the answer is still going to be largely involving this, and then what do I do with this guy? Okay? So that's the last thing we're going to do today. We're going to derive another formula. All right? So this is our goal. Like, we can't do this yet. So here's what we know. And we're only using f of t's that are of exponential order, one of the big four, right? We know that we're not gonna get crazy, well, not that crazy, not yet. Okay, so here's what I'd like to do. I want to find the derivative with respect to s, because technically this is a function of s. Oh, so that means I'm really doing the derivative of this integral.
Yeah.
Now the weird thing is the integral is a function of, I'm integrating a function of t, but my final answer actually is a function of s. Can I work the differential operator into the integral?
Yes.
Yes, but how will it go in?
As a partial because
Good,
the function is a
because I'm differentiating with something other than t, so I'm within the integral itself, I'm now going to treat s as a function. And I want to take the derivative with respect to s, but I also have a t, so it's, when you have partial derivative notation, do you do derivatives different? No, it just means you had more than one variable, that's all. But when I put it on the inside, you're exactly correct, it's going to look like that. Of e to the negative st of t. Y'all with me on that one? It can't be an ordinary derivative with respect to s when not t is the independent variable already. And before we get weirded out by going, but we've been treating s as a constant all of this time, and you're absolutely correct. You're absolutely correct. You're absolutely correct, but haven't we done this in Calc 3? In this integral, how do I treat y? Y is a variable, no question, but I treat it in the integral as a constant because I'm integrating with respect to x. And over here I'm treating x as the constant because I'm integrating with respect to y. Oh, okay.
But these are functions, but that's an operator. So do you just?
Well, no, s and t are variables. It's just my integral I'm integrating with respect to t. In this integral I'm integrating with respect to s. So within the integral I'm treating everything that's not an x as a constant, just like you do with partial derivatives. I have a bunch of variables, but the variable I'm differentiating with respect to is the only one that I treat as a variable. I treat all the other ones as constants for the purposes of that one step. So right now, this answer here is 1/2 x squared times y. This answer is 1/2 y squared times x. X and y are both variables. S and t were always both variables, but because the integration was with respect to t, we've treated s as a constant. S isn't a constant. If s were a constant, why would I ever need to say things like this? No, s is a variable. I'm just not integrating s. Oh, but now I want to differentiate s. So, this is not a hard derivative at all, is it? What am I going to get?
Negative s
Negative
e
s
to the.
Careful, you're differentiating with respect to s.
yeah.
Okay, so.
So negative t.
Negative t. That's it. That's it. That's your entire result is that guy right there. Okay. How about I rewrite this? I want to put the t's together because they like hanging out. They're good buds. Well, shoot, isn't that the Laplace transform of t f of t? Huh. Okay. That's kind of interesting. That was fun, right? In fact, it was so much fun, we want to do it again. I want to take a second derivative.
Wait, that's the answer. But
What's that?
that's. Oh, that integral
That was the derivative.
is what we were
The
looking.
derivative of this,
Is that?
I mean, we just followed it to the bitter end. Let's do another
Oh.
derivative.
Oh, I see.
Let's do I'll write it like this. Well, that means what am I going to be differentiating?
S again, twice.
So I'm going to differentiate a second time, so technically I'm differentiating this result right here. Agreed?
Yeah.
Is everybody okay? Can I just start from here? I'm going to differentiate this result right here. When I do that, won't I just get another T?
Oh, that's supposed to be an E on the ST.
Oh, thank you, E to the. When I do that, I'm just going to get another T, aren't I?
Yeah.
But what will happen to the plus or minus sign?
So this
It'll
becomes
alternate.
false.
We'll go back to positive.
Yeah.
So now this will give me T squared,
Yeah.
but I'm going to throw it over here.
So the signs alternate, you just increase in power.
I need to do this a bunch more times. I've done it 2 times. I need to do it n minus 2 more times,
Oh,
so that I can say I've done it n times.
So then,
But Dushanth had a good idea
Would it
there.
just be
The
negative
next
one?
one's going to be negative, isn't it?
Yeah.
And what's going to be the exponent?
just a
3.
higher
Yeah,
power
but what's
one.
the one after that going to be? Oh, you guys know this movie.
So is it -1 to power?
So here's what I'd like to know. Wait a minute, wasn't that my goal? Isn't that what I said our goal for the whole rest of the class was that? Can you tell me what it is?
-1 to the N. T to the N. Oh wait, go. F. F to the N or the N? F.
If I want to do the Laplace transform of t to the n times a function, it's the nth derivative of the Laplace transform of just my regular old everyday function.
Okay.
But other than the exponentials, n derivatives might be a lot of work. So we're rarely going to go past 2. Right, think of the cosine, right? What's the cosine? S over s squared plus k squared? That's an easy first derivative. I don't know, by the time I get to about the 5th or 6th derivative, that's probably getting pretty gnarly, right? So don't worry about that. Understand the process. We're going to do a whole bunch of examples now. But this is an incredibly cool formula. I mean, look at that. The nth derivative of this. This is for exponential. This is for sine and cosine. Yeah, this could be for t to the n, but I don't really doesn't make sense to have t to the n and then do t to the n here. But you got the right idea, because now we actually know the formula for t to the n. So let me see. Let me go over here. Can I write myself any examples? Yeah. Let's do one where we are actually already know the answer. Now, on day 1, we never actually did the Laplace transform of t. I just gave you, we did the Laplace transform of 1, but the Laplace transform of t, it's one integration by parts, right? It's not terrible. T to a higher power, that was terrible. That's why I went ahead and gave you the formula. I said we're going to prove it later, right? I gave you sine, I gave you t to the n, we derived exponential, we derived cosine. And those are the only 4 you ever actually use. But now we know all of them, and I'm not going to ask you to derive sine. You know what it takes because it looks just like the derivation of the cosine. Right? That's why the answer is so similar. But it would have been too much work to do anything beyond t to the first power. Even t to the second power would have been hard. But now we know t to any power because we didn't do it by integration. We did it kind of a more clever way. So let's do this one. We already know how to do it as an exponential shift. Is that correct? But I don't want to do it as an exponential shift. I want to do this as negative derivative of the Laplace transform of e to the 3t. That's what we just showed. Okay? What is the Laplace transform of e to the 3t.
1 over s minus 3.
Everybody agree with that?
Yes.
And so what would this be?
But
Think of that to the negative first power. So
do you
this
not
would be
include restriction with this one either? Or do you do that at the end?
always at the end.
Always at the end, okay.
If I think of this as s minus 3 to the negative first, then my answer is going to be just 1 over s minus 3 squared.
Yeah. Times negative 1.
And now we already have the negative there. Sorry. That's where I throw in the restriction, right there.
All right.
Now, if I thought of this as a shift, what's the Laplace transform? I want to do it two ways. What's this?
1 over.
Isn't this just 1 over s squared?
Yeah.
So if I do the shift, it's 1 over s minus 3 squared. So here's an example of one I could have gone either way. Okay? But isn't that kind of cool that we got the same answer regardless? Now, if I gave you one of the functions as exponential, the shift is easier. I didn't have to take a derivative.
Sorry, you're saying we're getting the same answer from two different functions by...
No. We're doing this one using the technique we just derived.
Yes.
And I said, think of this as the exponential shift. This is the Laplace transform of t, and now I'm doing the exponential shift. This is last week.
Oh,
Exponential
okay.
shift.
It's just the bottom portion.
Both answers are this. Because
Okay.
this is the Laplace transform of t, therefore when I do the shift of 3 units, that's what the exponential shift
Which you
would
get
be.
that answer over there. Okay.
I get that. So, two different points of view. So if it was an exponential shift, I would go with the exponential shift. I'd rather not take multiple derivatives. You with me on that one? That to me is kind of an oh-duh. When do I have to take derivatives? Well, I'm glad you asked.
Cosine.
There's only two ways to do this. One is by integration. Do you really want to do that one by integration?
No.
I don't. Two integration by parts. Neither one of them a lot of fun. Or I can do what we just learned. Let's try what we just learned. Okay? Somebody had a question here before I started.
Just the shift you could do whenever there's a product of two functions?
No. When one was exponential. Yeah, the shift came from the exponential. We derived that one, I want to say, was that, actually, no, was it Monday or Wednesday's lecture? I lost it.
Wednesday.
It was last week sometime. That's too far back. I don't remember.
Oh, yeah.
So this one, I can't do a shift. And I certainly don't want to set up the integral, right? The integral would be scary. So what do we want to do? We want to do this one right here. So this would be two derivatives of the Laplace transform of what?
Your sine function.
Of the sine function. Oh,
Please look at that.
okay. So let's do this in stages. First of all, what's the Laplace transform of the sine function?
Is that the 1 over?
4
I don't
over
remember.
s squared plus 16.
It's the S.
4 over s squared plus 4 squared. I'm going to go ahead and write 16 because it's going to show up. Now I got to do two derivatives of this, so I think it's easier if I wrote it like this. I can't do two derivatives at the same time. Does that make sense?
Yes.
Do the derivative, and then whatever you get, do the derivative again. You can't simultaneously do two. Now the first derivative is easy. First derivative is pretty easy. You don't have to do anything clever. You should be able to write the first derivative down without doing a whole lot of work.
Negative 4 over s squared plus 16 squared.
So what's the first derivative?
Is it like
s squared
plus 16 squared?
squared,
And then negative.
negative 8s on top. Some of you aren't aware of a really, really simple formula. I show this probably day 6, day 7 of Calc 1. And I'm going to show you guys this because this is a good one to know. Do you ever take reciprocals and take the derivatives? Yeah, and all of you use quotient rule. I said, why? It takes twice as many steps, and half the time we get the wrong answer anyway. The answer to this is negative f prime of x over f of x squared, which, by the way, is what you'd get if you use the quotient rule. If you use the quotient rule, bottom times derivative of top is 0. minus top times derivative bottom over bottom squared. When you're differentiating a reciprocal, because then the next thing we did was we did the derivatives of the trig functions. And this is the easiest way to get things like cosecant and secant, because they're reciprocals of known functions. So all I did was said, okay, oh, pull the 4 outside if it makes it easy. What's the derivative of the bottom? 2s. Negative 2s times 4 times that squared. Now I got to use quotient rule, don't I? Or do I?
No, product rule.
Product rule would be easier. Another one of those simple rules that I drill into my calculus students' heads is whenever your denominator is something raised to a power, write it as a product. It will always be easier. It'll be about half the steps. Yes, it's absolutely correct to use quotient rule, but you're going to spend half the time simplifying. So how about if I redid this like this? I know it's the same thing, but now it'll be easier to do this as product rule. So, first times derivative of the second. Right? Plus the second times the derivative of the first. This is the answer to the original question. It's just not in a very useful form. I would really rather have this be one quotient. So, give me a common factor.
Should it be
Did I lose something?
positive 8 or in the front because it's negative 8 times the negative 2?
Right, it should be negative 2.
Did I?
We're
Yeah.
at the
Oh, right
beginning.
there.
There, it's
Yeah.
a negative 2.
Thank you. That should be a negative. Yes, you're right. That should be a negative 2. That's still a negative 8.
Yeah.
What's common? So what's my greatest common?
That's
Well, factor for the uninitiated, divisor for the people who have taken discrete math, right? Divisor is such a cooler word, right? The same thing. What am I factoring out of it? Which power?
Plus 16 all squared.
Only one of them can work.
Negative 2. I don't know.
What's the rule for when you have two different exponents?
Factor
You have to
plus
take the
smallest.
small, always the smaller.
Yeah.
So what's smaller?
Negative 3.
Negative 3. No. We sometimes look at the wrong one, don't we?
Mm.
So I have 16s times 2s, that's 32s squared. Over here I have 8 times an entire factor that's left. Because I pulled out negative 3, right? So if I do that quick multiplication, I get back to there.
Yep.
So this is 32s squared minus 8s squared minus 128. So that looks like 24s squared minus 128 over s squared plus 16 to the third power. I don't think we can do anything more with that.
12 gamma.
Do you agree with that? Now, are there any restrictions? Well, yeah, it's a Laplace transform, so
This has to be greater than 0.
just 0. The only time it's not going to be 0, we realize now, is the exponentials. Things involving exponentials are the only time everything else is always going to be just 0. Okay?
I thought it was greater than 4.
No.
Because
There's no s minus 4 in the problem, though.
No, I was looking at the k value. I got confused. I was
Oh,
like,
yeah, that's not going to do it. Now, what if? What if that were a minus, just for whatever you were doing? Now I'd have a 4 and a negative 4. Now I got to figure out, that's a different animal altogether. That was what you did with the partial fractions problems. This is not that. This is not the partial fractions. So the rule is now, we now know how to do t to any integer power, positive integer power. We now know how to do it to halves, fairly simple notion. And now we can do t to a power times an exponential, a sine, or a cosine. It's kind of powerful that we now can do the Laplace transform of that. Now, going in reverse, too much work. First of all, if you were looking at this, you'd say, that kind of looks very sine-ish or cosine-ish. I'm not sure which one, but it's a third power, so it's got to be a couple of derivatives down the road, and now I'm going to try to work backwards. No, you're not going to go reverse on this one. Not on this. It's too hard. Could you go reverse on the exponential shifts, though?
Yeah.
Yeah, you did. We did that in class. The exponential shifts you could go in reverse because there was no differentiation or integration involved. But this involved two derivatives, and so I'd have to integrate twice, but that is not a trivial process. That would actually be pretty gnarly to say, what did I differentiate twice to get that? Do you all agree that that's, I don't know, you'd need a raise, right? You need at least to be on a higher pay scale to be asked that kind of question. It's not that it's a bad question, it's just that one's not going to come up. Not that version. All right? Shall we continue?
We shall.
Let me see. Do we have any good questions in here? I'm hoping we have some good questions. All right. I'm not asking you to derive any of the results, although that was a bonus question to derive a result. If you're ever deriving a result for a Laplace, that means you're going to do that improper integration, which means you're going to be doing an integration by parts, and it's kind of icky. But if I asked you that question, I would generally make it small. If I had to do this by integration, mathematically it is possible, but it would be a very long problem. Right? There'd be first of all, I had to break up into multiple integrations and then multiple integration by parts. So, is there any trick I can perform to make this shorter?
Can we
Factor
just,
out the t.
But will that help me in
can we just expand it?
Actually, yeah, maybe
Yeah,
expanding
I think Leo's right. Just expand it. I think that's a good starting point. I don't think there's any. I can't manipulate the algebraic statement to make it a simpler algebraic statement. But if I expand it, what will I have?
T to the 4
4
minus 6t cubed.
plus 19.
Okay. Then can I then treat it like this is whether you rewrote it? This is what you're at least doing in your head, I would hope. All right? When you differentiated a whole bunch of terms, I would hope you didn't rewrite it as a whole bunch of derivatives, right? I'm adding a whole bunch of derivatives and I factored in all the coefficients. But that's what you did in your head. You rewrote it in your head as you took that and you rewrote it mentally as this, and you're going to do them one at a time. I don't need you to rewrite it, but you have to understand that's actually the only way to do this problem is to break it up into pieces. Because if you're not going to break it up into pieces, then you're saying I'm going to integrate the whole thing. No, please. Remember, I have to grade these. Ruin the rest of my afternoon making me look at this for an hour, right? No, I want this to be simple. So, first one.
4 factorial over s to the 5th.
Sure.
S to the 5th.
Yes.
See, my S and my 5 actually don't look the same. Well, at least not to me. Okay, the next one.
Minus 6
3
times 3 factorial over s to the 4th. 9 times 2 factorial over s to the 3rd.
Now, because the factorials are relatively small, I'd combine them in this case. If you've got a really large factorial, no, just leave it as a large factorial. Right? That's only 24. That's only 6, so that's 36. It's going to be 18. That one I would go ahead and then I'd throw in the disclaimer at the end. That wasn't that bad. Agreed? So does it ever get bad? Yeah. I would probably opt for rewriting it. In fact, I'll call it the 6.
6 to the 6 t to the negative 1/2.
I would write it like that because that's the way we wrote our formula. We didn't write 1 over square root of t, did we? We wrote t to the, did we do t to the half or negative half? I can't remember.
Half.
We
Oh, wait.
did t,
Oh, wait, no.
sorry, which one did we do?
T to the half.
We did t, I'm trying to remember now. Did we do t to the half or negative half?
We did T to the half.
Okay, let me, then I will put this, I'm gonna put this in the square root of t. Sorry. Okay, I'll do it. And then,
Oh, you changed it.
I'm gonna make it just a square. This would be t to the,
3 halves.
if it wasn't halves, you could write the problem. You just can't finish the problem, so you're not gonna be asked that. I don't think there's a single problem in the text that's gonna give you a weird, thirds or fifths or something. It's just not gonna happen.
Did you grab that 6 over root t from the textbook, or where did you grab that from?
No, I just made it up, because I'm looking at the textbook, the author introduces the formula, but also I'm looking at the problems in 7.1, and I realized she doesn't have any fractional exponents in the homework. She gave the formula, but there's no practice problems. That's why I threw that in there.
Cool.
I'm looking in 7.4, I don't think there are any either. Which is a little bit of a problem, because we learned a formula, but there's no examples of it. So, oh well. So, first one's easy. Let's write them using gamma stuff. Okay? So, what is each one now?
Is that gamma?
6 times gamma of 3 halves over.
So what did I show you guys? I showed you,
The gamma alpha plus 1 stuff.
We did t to the 5 over 2.
so the first one would be what?
6.
Now that I think about it, I probably should have left it as the negative half, because I did give you that result.
Yeah.
I was thinking for a moment I didn't, but I actually did. So what's the first one gonna be?
6 times gamma 3 halves over. What was the bottom one? Was it 3 halves? I don't remember.
S to the what power?
That was S.
3 halves.
3 halves. You're gonna have these written down right next to you. You're not going to memorize these, because if you memorize these, you can easily be off by 1, can't you? Right? Can I get these off by? In fact, more likely, it's the 4 and the 5 are gonna switch places. That's more likely error. Because you know they're not the same number, but you might forget which one's on top and which one's on bottom. Have them written down, right next to you. And then the next one is,
Gamma 5 over 2. S to the 5 over 2.
all right, go ahead and finish this off for me, please.
Does it work if we wanted to do like -5 halves? Could we keep using the gamma for that, or is -1 half is the lowest?
That's the bottom end of the.
Okay.
Root pi.
Because first of all, when we did the actual integration, the substitution, that's the lowest one it would have worked for us. But even the higher ones, I said if I had done thirds or something and I used a u cubed to use the fourth, I'd have run into a brick wall on trying to do the parts. So it's kind of a magical process that the t to the negative a half was the only one that could show up in the integration and I could follow through.
Okay.
Yeah, so that's literally your bottom line. Now, the reason that's important is t to the negative 1/2 isn't of exponential order, but I can do it. That is really the exception. So I said, if it's of exponential order, we absolutely can do the Laplace, but it's possible that we could have something that's not Laplace and still do it. There's a lot of theorems that if this, then this, but the conclusions still hold, even though the premise didn't.
Yeah.
Yeah, there's a lot of times the premise didn't hold, but the conclusion still worked. But it's if the premise holds, the conclusion's guaranteed. That's the difference. Okay.
But it wouldn't work to say like the gamma of -3 halves.
Yeah, that one won't.
Okay.
Yeah. So we could.
We could
no,
do
no,
the,
we
could
could
do the
write
gamma,
the gamma
but
function.
we couldn't do the exponent on the bottom.
Right, we'd be in trouble at some point. We wouldn't be able to carry on because it's going the other way.
So
Remember, you're subtracting.
Oh yeah. Okay.
So you could
Okay.
really. It comes down to this. This is true, but what was the bottom line for alpha? Do you remember?
Had to be 1/2.
Had to be greater than -1.
Mm.
That was the bottom
Okay.
line. Okay. That was, oh, okay, so I can't do gamma of -10 or -20,
Yeah.
because the integration, it goes back to the integral.
Okay.
We would have run, because it's the parts that won't work. So the gamma function, it didn't have to be an integer, it didn't have to be halves for me to write it, and to write that recursion, but there were restrictions on alpha. So alpha couldn't go to the left forever, it could go to the right forever. All right, does anybody have an answer yet?
Yeah, those
Yeah.
numerators were 3
square root pi over s to the.
Wait, slow down, sorry. So the first one is what?
It's like 6
3
times
square root pi
or whatever.
3 root pi.
Over s to the 3 halves.
Does everyone agree with that answer? Good, okay, we all agree. I'm gonna do my part.
Perfect.
I'm gonna go a step further. I know, I'm a chancer.
You're giving too much.
It's a 3 again.
So 3 halves, 1 half, and it's just a 3?
Yeah.
Yep. Is there any benefit to factoring this?
No, but why not?
I'll leave it at that. It's never wrong. I don't know that it would have any use though, because it would be hard to work backwards. Do you agree that going backwards would not be an easy thing? Now, we don't do a lot of going backwards on this type of problem, although we kind of know where it has to come from, because you see this and you see this. But I would not ask you to go backwards on this one. Okay?
Has to be greater than 0 for this one as well?
I'm sorry?
S has to be greater than 0.
Yes, thank you. Let's not forget, we tend to do this. The only wonky error that's gonna occur on the next exam is some of you are gonna forget to put the restriction on every single Laplace, and you know it's gotta be there. Why do we have to do it? It's redundant, because if this is not true, then this diverges. This doesn't equal this. It only equals this if this is true. And sometimes we forget that restriction is kind of astronomical, because it goes back to the integration. E to the -st will only converge if st is positive. Right? If st is negative, then the e to the -st is going to grow to infinity really quickly. It's going to diverge. So I have to have that restriction in there.
If we do a Laplace transform, we get our first result, and we write our restriction, and then we start simplifying and
But just write the restrictions at the very
at
last.
the very end.
Yeah, just do it at the very last, because I think it'd be safer to say, what if we're doing one, let's say we had a couple of different shifts, like you did a partial fractions decomposition. And so you have an s plus 3 and s minus 5. Write down each restriction individually, and then step back and say, okay, I need the one that all of them is true at the same time. Does everybody agree with that? Which one is always true at the same time, so which one is it? The biggest number or the smallest number?
Biggest.
Yeah. Where do they all overlap? It's the biggest one. Does that make sense? Okay.
Is it possible you just walk us through those steps? Because
Yeah, I was relying on you guys who wrote down things, but some of you didn't. So let's do the second one, because that had more going on. So let's just do this piece right here. Because the rest of the stuff, these two terms are not going to change. They're going to stay there for the duration. What do I need to do? Well, I need to apply the gamma recursion. What's the last gamma function I'm going to have written down?
1/2.
1/2. I can't go past 1/2. And the gamma recursion is that. Now, here's the mistake a lot of us make. We put the alpha plus 1 here, like a factorial. And you can all understand how that would be an easy confusion. This, if alpha is an positive integer, this is alpha factorial. Because it's alpha times alpha minus 1 factorial. So this is going to equal, I think it's easier if you write that first. Then you remember to put the same number here. Then you remember to put the same number here, and now I'm done. So it's 3/4 root pi, but you already had a fourth, that's why it's 3 root pi.
Okay, thank you.
Does that help?
Yes.
By the way, don't do this in your head. No, write out the steps. If you do it in your head and you have any error, you're never going to figure out what went wrong, and you don't even know you have a wrong answer until later when you got the red pen, hacking it up and saying, what is wrong with you? No, always just write the steps out. I'm not going to ask you, just for fun on the next test, what's gamma of 651 halves, or something. No, I'm not going to ask you that. And no, you don't have to use any factorial simplifications. Well, you must the whole odds thing on top. No, it's not going to be that at all. No, I'd rather see just a number. I don't really want an unfinished answer if you can avoid it. Now, the S's are going to be on the bottom every time. No big deal. But isn't that all your Laplace transforms? Aren't the S's always on the bottom? Yeah.
Sometimes there's an S on top.
Sometimes there's when is there an S on top?
Only in that one function, the cosine one.
Cosine, or now when I'm doing, I've erased it. When I'm doing a Laplace transform of a t times a function and I have to take derivatives, like we just did a moment ago with the sine, there's a possibility because of derivatives that I know this term on top. All right, let's do a couple more practice problems and then I think it'll probably be good.
Can we do it piecewise?
Not for this isn't piecewise. Now, piecewise is a very, very specific, very special case. We do it because it can come up, and I want to be able to have a function. What I love about the unit function is that you can now take every piecewise and write it as one continuous statement. It's one function. You just got to know where the on-off switches is, right? But that's a very, very special problem.
Are you saying that these aren't piecewise because the Laplace transform is differentiable? Is that what you're saying?
Well, that is continuous.
Is that why this is not?
Yeah, piecewise are not continuous, right? Where I change definition, it's no longer continuous. I can have a break. Now, the piecewise can also do this, but it can also do this, right? The only break I can't have in the piecewise is on the domain. Now, that's in Calc 1, but technically, can I have a break in the domain on a piecewise? Can I say from 0 to 10 it's this, and from 20 to infinity it's this, and there's... You can say that it's 0. So in other words, when you have a break in the domain, you can just say it is 0 all that other time. So in a sense, you could argue there really is never a break in the domain.
That makes sense, but then you have a restriction for S when you find your final answer. But if this is differentiable everywhere, then
That's not differentiable, and that has to do with the integral converging or diverging. That's not about differentiability.
oh, this is different. Okay.
Yeah, that has to do with the definition of the Laplace transform is an improper integral with an exponential function in there that it's either going to infinity or going to 0. It's one or the other, right? So if I think of exponential growth goes to infinity, exponential decay is going to 0. I need to choose an x to force it into decay, in other words. So if I had made that s less than 0, then the original integral would have been infinite. And then all of this would be kind of a waste. All right, let's try a couple of these bad boys. How about... let's make that a 4 and a 2 and a
3 halves.
How's that? All right. I don't think it's necessary when you have multiple terms to force it into one quotient. I don't think that's necessary. I don't think that's entirely useful. It's always correct. If you had the sum of several answers right here, could we write this as one quotient rather easily? Yeah. I don't think there's any benefit, though. I really don't think that makes anything easier to make this one quotient with a common denominator. Okay? There are exceptions. If you have a bunch of rational functions that combine easily, sometimes writing it as one quotient is superior. Because when you were doing the inverse Laplace transform, you were doing inverse Laplace transforms of one quotient where your denominator might have been the product of multiple factors. So you now had to do the partial fractions decomposition. So if I gave you 4 quotients that actually cleaned up very nicely as one, that might be a more useful answer. I just have to know how to navigate. But it's not always necessary that you squish everything together. No matter what, my final answer can be written as one quotient. I'm going to guarantee you that. But is that answer necessarily a better answer or just another answer? I don't know. So, what's the first one going to be? I'll just write out what it is.
What's the derivative of s over s squared plus 4 or 2 squared?
I'll put it 4 because I got to differentiate that bad boy.
Three over s squared plus 9.
you wanna do 3 derivatives?
Yay.
Or do you wanna use the shift?
Use a shift, please.
And then what will that be?
It will be -6 times 3 factorial over s minus 2 all to the power of 4.
Good, good. Now, I could have done that by taking multiple derivatives, because the derivatives wouldn't have been very hard, because they'd be derivatives of s minus 2. Does everybody agree with that? Now, we're not nearly done. Closure rule on this one, right? So, what do we got? Bottom
Times 2
1 minus top times 2s over s squared plus 4 squared. Not fun. So what is, does this clean up very nicely? S squared plus 4 minus 2s squared.
Oh, it's just
It's gonna be negative s squared plus 4?
yeah.
Do you like negative s squared plus 4, or would you rather have 4 minus s squared? Or does it matter? What would you rather write?
4 minus s squared, I guess. I don't know.
Does it matter, first of all?
No.
No. No, I'll leave it like that. Now, times 4, I gotta work that in at some point. Not worried about it yet. I'm pretty certain I've done everything correct, okay? Next one, this one's a little easier.
Oh, it's just 2s minus squared plus 9 all squared.
Again, we'll clean that one up as necessary. Obviously, just gonna distribute. And then the last one, 6.
Negative 36.
Now, could I put this over 1 common denominator?
Oh, that's s minus 2 for the.
Oops, oh, thank s minus 2, thank you. Can I make this over 1 common denominator? Sure, but it'd be that one times that one times that one. You really want to multiply the top out? Do you realize how awful that would be? It would be correct, but I think that would be just really messy. Okay, so far so good? Now, the bestest finalist answer I would get, I would distribute the 4, I'd distribute the 2. And what about restriction?
S is greater than 2.
So the first one's greater than 0, second one's greater than 0, last one greater than
2.
2, so that's the one we go with. Because that's the only one that covers all 3.
I need to make sure again. Can you talk about the shifting one more time? Because like I know it's like vaguely making sense, but then I don't get it.
It's back in your memory, way back when. I think we used an A.
Okay.
Assuming, let's assume this, by the way. Assuming that's one we know, a simple one, what does this do? Anybody?
So it gives s minus a.
That's it. So you know the Laplace transform of t cubed, right? It's 3 factorial over s to the 4th.
Yes.
Oh, but I'm doing the exponential shift, so I replace s with
2.
s minus 2. Because this was e to the 2t.
Okay.
So that we derived this. I didn't tell you that. We derived this, and it wasn't a complicated derivation at all. It was actually kind of clean.
Right, but this is only
When we did the formula, wasn't it -1 to the power of n times the derivative?
Did I? Oh, thank you. Leo's correct. Yes. Leo's right. We lost it. So, what does it show up?
-4 and -2.
Yeah, Leo's absolutely correct. Good catch. Good catch. It alternates. Now that throws us because I promise you I will not ask you past second derivative just because it becomes way too long-winded. Could I have done this one as a third derivative?
Yeah.
Yes. And by the way, all the derivatives would have been easy because it's just s minus 2 to a power. So the Cherenkov factor is always going to be a 1. But because that's exponential, you could have done this as 3 derivatives or just done it as a shift. Obviously, a shift would be a better way to go. Oh, but this is the new material. Should I practice it that way? Well, yeah, you can, but I'll discourage you by putting, I don't know, 300 or something. No, if one is easy and obvious, take the easy, obvious one. Don't. Yeah, yes, The first two, you have no choice. You have to do the derivative. There is no other way unless you wanted to integrate it. And then that's some gnarly parts, right? I don't want to do that one. I've shown you guys how to do it. You know, I suffered greatly, you know, and I'm done with that. All right, we are done. We have finished everything now that's going to be on the next exam. And just to remind, the exam is chapter 6 stuff, the power series stuff, and the exam is going to be Laplace stuff. You get to write down the big four. You're not going to be asked to derive them. It's now manipulation and use and your ability to go backward. That's still the more major one, to go backwards. The differential equation was just a nice little application of it. And that was not supposed to be terribly taxing. But the differential equation, I'm not sure I could design a meaningful problem that didn't involve parts. So that does tend to slow you down, right? We know that parts slows us down. I'm sorry, not parts, partial fractions. That's what I meant. And then when we're doing the Laplace in general, that's a parts. Those are really the only two you use. Now, I want to remind you, I want to go back a little bit because I got asked this question from somebody and they completely forgot that we had actually looked at it. So I want to do, let's say, an inverse Laplace transform of something of the following form, you know, s minus 3 squared over s plus 5 to the 10th power. Okay. Yes, I can do the regular old traditional partial fractions decomposition, and that would take me exactly 10 quotients in a 10 by 10 matrix. I can knock off one of the numbers. I can only knock off one, by the way. So now I can really make it only a 9 by 9 matrix. How should I attack this one?
Substitute
T equal
with
S
t
plus
equal s
5.
plus 5.
So yeah, the question is, which one do I want to manipulate? I want to manipulate the bottom. Yeah, not the top, the bottom. So if I said, this is scratch work. To me, this is just really nice because it works so simply.
Yeah.
So then S is t minus 5. So what do I have here?
T minus
T minus
8.
8.
I have t minus 8, and I need to square that. And now I'll put it back. This is not the only way to do it. I could have just said, okay, this is s plus 5 minus 8, and then square them separately. I just think this is easier. It's less thinking required. So why did I do all of that? Because that now means that I'm doing the Laplace transform of s plus 5 to the second power minus 16 s plus 5 to the first plus 5. Plus 64 all over s plus 5 to the 10th. Can I now cancel?
Yep.
Mm-hmm.
So I am 1 over s plus 5 to the 8th, minus 16 over s plus 5 to the 9th, plus 64 over s plus 5 to the 10th. Can we finish this problem?
Yeah.
Just a shift.
So the shift is 5 units to the right, so that means there's going to be an e to the what?
Negative 5t.
So my f of t is going to be e to the negative 5t, and by the way, I would just factor that out of the problem, just make life easier. Now, what are the rest of them going to look like?
It's going to look like
7
1 over 7 factorial.
Well, it's going to be t to what power for the
The
first?
7,
And the next one,
t to the 8,
and the last one.
t to the 9.
Now, are these on the bottom or on the top?
On the top.
Top. Now the coefficients.
1 over 7.
Well, if I do the Laplace transform on this, won't I have a 7 factorial be introduced? So what the textbook will tell you to do, and I'm a big fan, let's take it like this. 7 factorial, 7 factorial.